Hello, and welcome back to Elements of Chemistry. Today we're going to talk about how to do math with chemical formulas. Every science student is going to encounter some type of mathematical formula that's going to need to be solved for a specific variable. For example, in physics, quite often you need to solve F equals ma, and you need to solve for m or a. The key to solving these algebraic puzzles is to isolate the variable by doing the opposite operation. For example, let's look at F equals ma. If you need to solve this for m, you need to isolate m. So when I first started doing this, I would circle the variable I needed to isolate. So I would circle m. And you need to look at it. M is multiplied by a. Work it out down here. So I've got to undo a multiplication. To undo a multiplication, you divide. And what you do to one side, you do to both sides. Now, in the fraction a over a, the a's, or acceleration in this case, would cancel each other out. So we'd have f over a equals m. And then you could put in your values for force, your values for acceleration, and solve for the mass. In chemistry, quite often, you're going to have to solve something like with Boyle's law problem. P1 V1 equals P2 V2. This means that the first pressure in the first volume is going to equal the second pressure in volume measurements. If we wanted to isolate this for P2, so let's go ahead and let's try this one. We're going to go P1 V1 equals P2 V2. I need to isolate P2. So I'm going to circle P2, and then I'm going to look at what's happening to P2. P2 is being multiplied by V2. So to get it by itself, I'm going to divide by V2. And what I do to one side of my equation, I do to both sides of the equation. The V's will cancel out. V2, sorry, will cancel out. And I'm left with P1 V1 over V2 equaling P2. If we have a density problem, something like density is mass divided by volume. If I wanted to solve this one for mass, I'll notice that mass is divided by volume. So we have to do the opposite. If mass is divided by volume, to get that mass by itself, I'm going to have to multiply both sides of my equation by volume so that now the volumes can cross cancel out. So volume times density equals my mass. So to undo a division, you multiply. To undo a multiplication, you divide. What you do to one side, you do to both sides. Okay, so then it gets a little trickier when we have some things that involve addition and subtraction. Here's a common example for physics. Velocity is equal to the change in displacement over the change in time. That delta symbol means change, okay? So delta x would be x2 minus x1. Delta t would be t2 minus t1. And we can do this solving for any variable we're interested in. So let's say we're going to solve for x1. So we're going to write the equation expanded. Volume is equal to x2 minus x1 over t2 minus t1. Remember, we want to solve this for x2. So the first thing we're going to need to do is get rid of this down here on the bottom. So to do that, we're going to multiply both sides by that value. I'm going to work this in gold so you can see the difference. So I'm going to multiply this by T2 minus T1. And what I do to one side, I do to both sides. This is going to allow this to cancel out. Okay, I need to clean up some of my algebra here. I've got something I've got to distribute. So I'm going to have V multiplying by each one of those. So I'm going to have V T2 minus B T1 is equal to X2 minus X1. Okay, looks good. Now I need to isolate X2. So I have a subtraction here. To undo a subtraction, I'm going to want to add. to both sides. That allows that to cancel out. So I'm going to have B T2 minus V T1. I just switched to lowercase, that's fine. Plus X1 equals X2. A little more complex, but you can still solve it. You can plug in your variables and get the right answer. Now let's try one from, oh, sorry. I was about to say we're going to try one from chemistry, but that's our example later. So let's look at how to work the problems with the algebra. First, solve the actual problem. Solve for the variable of interest. Okay? Isolate your equation. Read your problem carefully and identify what you know. Choose the equation you want to solve. So is it F equals ma? Is it density is mass over volume? Rearrange the equation, and that's what we've been focusing here on, is how to rearrange the equation. And then substitute in your known values and do the math. Some students have trouble dealing with the x's and t's and all of the variables, and they just go ahead and put the math in first. You can do it that way. It's generally not as clean, but you can do it that way. The math is all good. So let's look at the volume of an object. We want to find volume. So volume is what I want to know. So I'm going to list that. Volume is my question mark. I know a mass, it's 125 grams. And I know a density is 0.95 grams per centimeter cubed. Okay, now this problem is kind of interesting. I can either use it by a formula or I could actually do it by dimensional analysis. So we're going to do this one both ways. Okay, I have variables of V, M, and D. And I know my density, so I'm probably going to need the density equation. Density is mass over volume. We like to say that density broke my heart because mass over volume kind of looks like a heart and you break it. So you get your mass over volume. It's just one way to remember it. Okay, I want to solve this for volume. Well, volume's in the denominator. And it's not always nice to solve for things in the denominator. So I'm going to get rid of that fraction. To get rid of the fraction, I'm going to multiply both sides by V. So density times volume equals my mass. Well, that didn't solve me for V yet. I still have V that I need to isolate. But now I can undo that multiplication by dividing both sides by the density. So volume is mass over density. I take my mass, 125 grams, divided by my density, 0.95 grams, doesn't want to write, grams per centimeter cubed. Now, if we look at the math and the units here, the grams are going to cancel out the grams, and I'm going to have 1 over centimeter cubed, which that's kind of a 1 over x situation, which is just x. So that leaves me a unit of centimeters cubed. Find my handy dandy best friend here to do the work for me. 125 divided by 0.95. Now let's look at our significant figures. By now you should be able to work with significant figures. I go back to my given. I have 3 significant figures here. I have 2 significant figures here, so I only want 2 in my answer. My calculator is showing 131.5789474. That's too much to write. I want 2 significant figures. You start at the big end of the number, 1, 2, look to the right. That 131 got around to 130 centimeters cubed. Now I said we could also do this with dimensional analysis. And the way we could do that is, see this fractional unit here? That can be a conversion factor. So we can take our given, putting it, my pencil doesn't want a pencil today for us here. We'll take our given, put it into our scheme, 125 grams. Now this grams per cubic centimeter, I know I need to cancel out grams. So the 0.95 grams has to go on the bottom and 1 centimeter cubed has to go on top. Grams will cancel out grams. And I have 125 divided by 0.95. I still get that same mathematical number. But this time we've got to realize this isn't a conversion factor. It's a measured value. It's a calculated value. So we still have to use it for sig figs, but we still get that 135 centimeters cubed. Okay, let's look at another one here. Find the new volume of a gas at 1.2 atmospheres pressure if the gas is compressed from a volume of 250 liters at 1 atmosphere. So we've read our problem. Let's see what we know. We want to find the new volume at 1.2 atmospheres. It's compressed from, that's our initial. So our initial volume, V1, is 250 liters. Our initial pressure, P1, was 1 atmosphere. We want to go to a new volume, is what we want to find. So that's my question mark. And I have a new pressure of 1.2 atmospheres. I look at my equation. P1 V1 equals P2 V2. I want to get V2 by itself. I want to find that final volume. So I'm going to need to divide both sides of my equation by P2. That isolates V2. I'm going to go ahead and put in my P1, 1 atmosphere. I'm going to put in my V1, 250 liters. My P2, 1.2 atmospheres. And that's going to equal my V2. The atmospheres are going to cancel the atmospheres. I'm going to get units of liters, which is what we want. I'm going to have 1 times 250 and then divide by 1.2. Now, 1 atmosphere has 1 significant figure. So my calculator came out with 208.33. Well, that's going to have to be 200 liters when I do my significant figures. Okay, let's try another example. Annie rode her bike to Susan's house at an average velocity of 0.4 meters per second. The distance to Susan's house is 1,275 meters. How long did it take Annie to get to Susan's house? Well, this one here, I'm going to actually do by dimensional analysis. See that unit? It is a distance per time unit, that 0.4 meters per second, and I know my meters. So I can take the 1275 meters as my given. For every meter, for every second, I go 0.4 meters. My meters can cancel out. I'm going to be left with time of seconds. So I didn't even have to use one of the other formulas here. 1275 divided by 0.4. Now let's look, 1 significant figure. So mathematically, this mathematically correct is 31887.5 seconds. But I want 1 significant figure, so that's going to be 3,000 seconds. Okay, 3,000 seconds is kind of an awkward number to remember or visualize. Well, I know that for every 1 minute, there's 60 seconds. So let's divide it by 60. And it's going to take about 50 minutes at that rate to get to Susan's house. Now we could have used velocity equals distance over time. We know our velocity. We know our distance. We can figure out our time. Doing it with resolving for equations, we're going to multiply both sides by time. The time will cancel out. Our velocity was 0.4 meters per second. Oops, we didn't isolate it for time, did we? Hang on, we jumped ahead. Let's go back. Now we want to get, for time, it's distance divided by velocity. There we go. Our distance, 1275 meters, divided by our velocity, 0.4 meters per second. The meters canceled meters, 1/seconds. And we come up with, for significant figures, 3,000 seconds, just like we did before. Either way works. Okay, here's a chemistry example I was trying to jump to a little ahead of time. 25,000 joules of heat energy, which have the symbol Q, is used to heat 100 grams, the mass, of a sample with a specific heat of 0.978, and we always put that leading zero in, joules per gram degree Celsius. If the sample starts at 50 degrees Celsius, what's its final temperature? And we've got a delta T to deal with. Okay, so we need to solve this equation for T final. So we can say that Q equals MC T2 minus T1. Doing some algebra here, because we want to solve this for T2. Well, let's clean it up. Let's divide both sides by MC. That cancels that. So Q over MC equals T2 minus T1. Well, I want to solve for T2. So I'm going to add T1 to both sides of the equation. Those are going to drop out. The T1s will drop. My pencil is, there we go. So we're going to have Q over MC plus T1 equals T2. Let's plug in what we know. We know our Q, 25,000 joules. We know our mass, 100 grams. Sometimes you just need to change a pencil. And we know our specific heat, 0.978 joules per gram degree Celsius. And we know our T1 at 50 degrees Celsius equals my T2. Let's do some cleaning up of units first. This joule cancels this joule. This gram cancels this gram. We're left with 1 over degrees Celsius. So that's a degree Celsius. So let's get out our handy dandy calculator and do some math here. We've got 25,000 divided by 100 and divided by 0.978. So this is going to give me 255, and I'm keeping all the figures right now in my calculator because I'm going to do that, plus 50 degrees Celsius. So if I'm going to add 50 to this, that's going to give me 305.62, blah, 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 degrees Celsius. Okay, 50, we're adding. Okay, so let's look at what we've got here. In this operation here, one significant figure. So that's going to round this number here. We'll round at the end. We'll just do it with the addition one here. It's kind of funky one. So one at the decimal place, we're going to call that 300 degrees Celsius. This is one of those questions when you get to your teacher and you want to ask them, do we round at the end or do you want us to round at intermediate steps? Each teacher does it slightly differently, and I don't want to tell you definitely do it this way. I would have had my students know that it's an addition subtraction problem essentially. I would have carried everything out did my addition, subtraction, and then rounded at the end. There is a school of thought that you round based on each major operation. You should still come very close to the same answer. I tend to do sig figs at the end. Addition, subtraction was that final step, chopping it off. So I hope this video helped and didn't confuse you. As always, stay curious, be kind, stay safe. Have a wonderful day, everyone.